What's up, everybody? Welcome back to Mathletes Corner. We are back on the iconic blackboard, and today we're going to be looking at the 2025 AMC8 Final Fives. So, without further ado, let's get right into it. So, of course, starting with problem 21, I would say this question was, other than problem 25, I would say this one was the hardest question in the Final Fives. So, the question says the Königsberg School has assigned grades 1 through 7 to pods A through G, one grade per pod. Some of the pods are connected by walkways as shown in the figure below. The school noticed that each pair of connected pods has been assigned grades differing by 2 or more grade levels. For example, grades 1 and 2 will not be in pods directly connected by a walkway. What is the sum of the grade levels assigned to pods C, E, and F? So that last part is really important. We want to look at pods C, E, and F because those are the most important ones. So first, let's take a look at F. Okay, I'll mark F. So F is adjacent to G, A, B, C, and E. So it's adjacent to everything other than D. So let's list all of the numbers from 1 to 7. So here, say 2 for example. 2 cannot be adjacent to 1 or 3. So that tells us that F is not 2 because F, there's only one number that is not adjacent to F. So F can't be 2. Similarly, F can't be 3, 4, 5, or 6. But when F is 1 or 7, it's possible because for 1, 2 is the only number that cannot be adjacent to 1. For 7, 6 is the only number that cannot be adjacent to 7. Now, the question is F equal to 1 or is it equal to 7? And it's kind of difficult to figure that out. So let's try looking at the other numbers we have and try to collect more information. So let's look at C. We know C is adjacent to A, B, F, D, and E. So the only number that C is not adjacent to is G. So that means, in the same way, C is either 1 or it's 7. So what does that tell us? That tells us that we don't need to find C and F. We just know that their values are 1 and 7. So I'll say 1 and 7 is equal to the set with C and F. And we want the sum of C, E, and F. And we already know that C and F add up to 8. So right now, all we need is E. So let's take a look at E. So we know E is adjacent to both C and F. So let's see what values E can be. So once again, listing the numbers from 1 all the way to 7. And we know that E cannot be 1 and it cannot be 7. And because it is adjacent to both C and F, it cannot be 2 and it cannot be 6. So E can be 3, 4, or 5. And now we have to figure out which of those three values E obtains. And we also notice that A and B are in similar situations. And in fact, they're in the exact same situation. A is adjacent to both C and F. B is also adjacent to both C and F. The key, though, is that A and B themselves are adjacent, which means that if one of them is 4, then that won't work because 3 and 4 can't be adjacent, 4 and 5 can't be adjacent. So that means A and B take up the values 3 and 5, or vice versa. So we know that E cannot be 3 or 5, and we know that E is equal to 4, and that gives us the answer C plus E plus F is equal to 12. So that's a pretty neat problem with a slight graph theory reference and some logic, basically. Now, on to question 22. A classroom has a row of 35 coat hooks. Paulina likes coats to be equally spaced so that there's the same number of empty hooks before the first coat, after the last coat, and between every coat and the next one. Suppose that there is at least one coat and at least one empty hook. How many different numbers of coats can satisfy Paulina's pattern? So let's start by assigning variables, just like we do in every other algebra problem. Let's say x is the number of hooks in each gap. So in this case, in the drawing here, that would be 2. So basically the number of hooks that are between two consecutive codes. So I'm going to say X gap just as a short form, and I'm going to say Y is the number of codes. So now what can we say? We can say that Y, so the number of codes, plus the number of empty hooks is 35. How can we count the number of empty hooks? Well, we know that if there's Y codes, then there are Y plus 1 gaps. So we get Y plus 1 times X. Let me explain that a little bit. If we have a code here and a code here, we get 3 different gaps, right? Now, every time we add another code, we're getting an extra gap. So that's how we know that when we have Y codes, there has to be Y plus 1 gaps. So here we see that Y plus 1 times X is equal to 35. Now let me copy that equation down here. Y plus 1x equals 35. Now, something pretty clever that we can do here is add 1 to both sides. And you'll notice here we have y plus 1 times, or plus rather, y plus 1 times x equals 35 plus 1, which is 36. Now, we can factor this, and we can say that y plus 1 times x plus 1 equals 36. And now, this is just a matter of how many factors does 36 have? Well, we know that 36 is equal to 2 squared times 3 squared. So the number of factors of 36 is 9. But we have to remember that in the problem, so going back to the problem, it specifically says, suppose there is at least one code and at least one empty hook. So what does that mean? That means both x and y have to be positive. Neither of them can be non-positive. Neither of them can be 0 or less. In this case, if x is 0, y would be 35. And that's a solution that we're counting if we say 9. Similarly, if y is 0, x is 35, and that's a solution that we're counting. And we don't want to count those, so we'll subtract off 2 to get our answer of 7. The problem seems difficult when we use the complex algebra, but we could just imagine it as adding a code at the end, and now we have various groups that are all equal for each code. And so the number of codes has to be a factor of 36 if we include the additional code that we added in the beginning. So let's get on to the next one. So problem 23. How many 4-digit numbers have all 3 of the following properties? The tens and ones digit are both 9. The number is 1 less than a perfect square, and the number is the product of exactly 2 prime numbers. So let's not worry about the third condition for now. Just the first 2 really stand out. And why do they stand out? Because if a number ends in 2 nines, then the next number will end in 2 zeros. And we're given that the number we're looking for, or well, the ideal 4-digit number with these properties, has 2 nines at the end. And it's 1 less than perfect square. So that means the perfect square ends in 2 zeros. Or in other words, the perfect square is a multiple of 100. And since it's a 4-digit number, we can simplify our possibilities. And we don't have to look at all the 4-digit numbers. We only have to look at the numbers that are 1 less than a square, which is a multiple of 100. So what are those numbers? So we have 40 squared minus 1, because 30 squared would be 900. That's not quite a 4-digit number. 40 squared is 1600, and that is a 4-digit number. So we have 40 squared minus 1, 50 squared minus 1, 60 squared minus 1, all the way up to 90 squared minus 1. Now, evaluating these numbers and then factoring them would be one big job to do. Now, evaluating these numbers and factoring them would be quite some work, and we don't want to do that. So what we can do is difference of squares. So here we can factor it as 40 minus 1 times 40 plus 1. So here we can say 39 times 41. Here we can say 49 times 51, and so on and so forth. And now we can go back to the question and look at what the third condition is saying. The number is the product of exactly, that's the key word, exactly two prime numbers. So that means this 39 is not prime. So that one is not included. In the next one, 49 is not prime. That one's not included. 59 times 61, both of those are prime. So that one is included. 69 is not prime. 81 is not prime. 91 is not prime. So we can conclude that there is only one such four-digit number. On to the next one. Okay, so problem 24 says, in trapezoid ABCD, angles B and C measure 60 degrees and AB is equal to DC. The side lengths are all positive integers and the perimeter of ABCD is 30 units. How many non-congruent trapezoids satisfy all of these conditions? So, of course, as we do in every geometry problem, we'll start by drawing our diagram. A, B, C, and D. And we're given AB is equal to DC. These two angles measure 60 degrees. The side lengths are all positive integers, and the perimeter of ABCD is 30 units. How many non-congruent trapezoids satisfy all of these conditions? So, the obvious or the natural thing to do here is to drop these altitudes from A and D. And why are we doing that? Because we make 30, 60, 90 triangles. And there's nothing better in a geometry problem than 30, 60, 90 triangles. And we get two of them. So let's start assigning variables. We can put x here, we can put x there, and we know that both of those are equal because it's an isosceles trapezoid. We put y here and we put y here. Now, because it's 30, 60, 90 triangles, these two are both 2x. And now we can say, when we add it all up, 6x plus 2y equals 30. And the obvious thing to do with this equation is to divide by 2. So we get 3x plus y equals 15. Now, we also want to make sure that we don't create any quadrilaterals that are not trapezoids or something that isn't a quadrilateral at all. So let's make sure that we satisfy all of the conditions given to us in the problem. So when x is positive and y is positive, we have no problem. Our problem comes when x becomes 0, because when x is 0, we don't have a trapezoid, we have a rectangle. So our only solutions are when x is equal to 1, 2, 3, 4. And we may notice that in the problem, our maximum answer choice is 4. So you could just bubble in 4 and move on. But just for the sake of explanation, when x is 5, y becomes 0. So what happens here when y is 0? These two 30, 60, 90 triangles come together and you don't have any space in the middle. What you end up with is not a trapezoid, it's a triangle. It's an equilateral triangle too. So now that we've gone through that, we can box our answer 4 and move on to the next question, which is a fantastic combinatorics question. So problem 25 says, Michaela finds all the possible ways to draw a path in a 5 by 5 diamond-shaped grid. Each path starts at the bottom of the grid and ends at the top, always moving 1 unit northeast or northwest. She computes the area of the region between each path and the right side of the grid. Two examples are shown in the figures below. What is the sum of the areas determined by all possible paths? So just so that we all understand what's going on here, she draws a path. So let's use the examples given here. She draws this path, and all she's doing is counting how many squares are to the right of the path. So I'll reduce that thickness. And how many squares are to the right of the path? So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And that's how we're getting that 11. Same thing on the right example. We have 1, 2, 3, and then here we have 10. That's how we get that 13 there. Now, what the question is asking us for is over all of those paths, over all of the paths that Michaela can make on this grid in this way, what is the sum of the number of squares on the right for all of the paths? That's what the question is asking us. And that's a lot. Obviously, that's a lot to count, so we don't want to bash through this. So we're going to look for a clever solution. Now, something that we would like to do in this is look for some symmetry. But before we do that, let's see how many paths can she make? Well, we have a 5 by 5 grid, and we know that if we have an m by n grid, it's m plus n, choose m, or m plus n, choose n, number of ways to go from one corner to the other corner. So, in this case, there are 10 choose 5 different paths because 5 plus 5 is 10, and then we do 10 choose 5. And that comes out to 252. And as I said before, we don't want to count this area over all 252 paths. So something that we would like to do is pair them up. If we pair them up such that the sum of the areas is always the same, then we could just say 126 times that constant area for each of those pairs. And what's beautiful in this problem is that we can do exactly that. So let's see how we could make these symmetries. So I'll erase these dots here. Now we see this path here. Now the obvious reflection, or the natural reflection that we can do in this case, is to reflect it over this. That's not a good line. I'll redo that. It's to reflect it over this. Now, why do we want to reflect it over this? Why is this the natural reflection? Because the whole square maps to itself, and the actual grid is not altered. The actual grid will remain the same. The path will change, but the grid will stay the same. Now, what happens to this path? So let's map out this path, or it wouldn't go there. It would be reflected. So it would go here and there. Now, let's count how many of the squares are on the right of this path. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now, when we take 14 and add it to 11, what do we get? 25. What else is 25? Other than the problem number. Yeah, it's the number of squares in the 5 by 5 grid. Now let's do the same thing on the right example. If we draw out this path, then how many squares are on the right? Well, here it's just a 3 by 4 grid, and it's 12. We add it to 13, and what do you know? It adds right back up to 25. Now, why does that happen? So, if I erase this path, all of the white squares here become the gray squares on the right, because all of those white squares are reflected onto the right and all of the gray squares are reflected onto the left. So the initial gray squares that were pushed to the right are now being pushed to the left, and the squares that were being pushed to the left are being pushed to the right. So we can pair them up in this way to get our total of 25 for each of those pairs. And now we know exactly what we want to do. We can take the 125, we can pair them up, so we have 126 pairs, and each of those pairs add up to a total area of 25, we can say that's equal to 63 times 50 for our final answer of 3150. You can go back here, and that is option B. So yeah, that's an amazing combinatorics and a little bit of geometry problem. So yeah, that's all for this video. Thank you for watching. Don't forget to hit that like and subscribe button, and we'll see you next time here at Mathlete's Corner.